So beyond the think tank, we also have a fund where we launch companies and incubate companies. We're very different from the Y Combinators of the world in that we're high touch, low volume, meaning we actually, instead of giving 25K or 100K, we give 1.5 to 3 million to startups. And these startups, we do everything from helping with business design and go to market. So the co-founders of the Hive have many years of experience of bringing companies from the very grassroots ground up. And then they also have a technical team such as myself, which helps with architecture, have a lot of big data back-end expertise. And we don't go after companies that are doing infrastructure, so we're not trying to start the next Cloudera or Continuity. We're actually building companies that are the applications on top of these. That's why we partner with companies like that, and then we go and build the application on top. So whether or not it's security, CRM, these type of things. Automotive is a big area we're looking at. Media and advertising is also an area of expertise. So all of our startups are hiring. We have so if you're looking to get into a startup, please come talk to us. And if you have the what?
Ravi's here.
Oh yes. Oh, and see, Ravi's hiring. He's one of our companies. Perspica's here. They're also hiring. And then also if you're an entrepreneur and you have an idea and you want to get it funded and you think it's worthy, come definitely email us and it's actually info at Hive Data for one more. So info at Hive Data if you've got a company idea. And for tonight, I'm also going to introduce Tom White, who many of you all probably know from the Hadoop, the Definitive Guide, and it is the Definitive Guide. If you all have read it, and Tom's the right person to have written this book. He's one of the foremost experts on Hadoop, going back to 2007, where he's been an Apache committer since the very beginning. And there's some details a little fuzzy, but I did see a post where he was hacking on Nutch at the very beginning and said, "Hey, I think I got this thing working in distributed modes." This is way back. 2006. 2006. Also, he's now a software engineer at Cloudera, where he's worked since the foundation of Cloudera, and he's been writing for articles for O'Reilly, Java.net, IBM's developerWorks, and he's got a mathematics degree from Cambridge and a master's in philosophy from University of Leeds. Welcome, Tom.
Thank you, Lance, for the introduction, and thank you everyone for coming. Today, I'm going to be talking about building big data applications on Hadoop, and I'm going to introduce Kite, which is an SDK for building data applications. So Lance just mentioned 2006 when Hadoop was a little different, and this is roughly what it looked like in those days. I'm not sure if the version number is exactly correct, but this is a data application on Hadoop circa, I don't know, 2007, something like that. So the first line is you've got your big data, it's a text file, you pipe it into Hadoop, so it was very hard in those days to get your data into Hadoop. It was really only one way, through the Hadoop fs command. The second line is the processing. That's where you run your MapReduce job over the input data and get some output. And you had to write your MapReduce job in Java. It was quite complicated. It was quite low level. And then at the end, after it had run for minutes or maybe hours, you would retrieve the output, if it was small, onto your local file system, and then maybe do some post-processing. So that's what it looked like several years ago. And the characteristics of that way of working were that it was really only batch applications that you could run. Jobs took a long time to run. You there were often trade-offs that you had to make. If you wanted something more responsive, you would have to have smaller jobs that only worked on a small part of the data set. So there were some complicated trade-offs that people had to make there. And if you're actually running these programs, you had to do a lot of low-level coding yourself. You had to worry about things like the file format. I showed you a text file. You could use binary, but you had to use this thing called writables, which was Hadoop's kind of binary format, which was quite verbose. You had to do quite a lot of work to get that to work. So that was the serialization you had to worry about. Partitioning, if you think about how your data was coming in, you would often want to partition it by time in some way. So you would have year, month, and date, and how you managed that was completely up to you. You had to make decisions, design decisions, and you had to code all of that yourself. So if we come back to today, things look very different. This is what a Hadoop stack looks like today. This is Cloudera's diagram of CDH. And the first thing you might notice is that it doesn't have labels on it which say MapReduce and HDFS, Zookeeper. All of those things are missing from this diagram. It's actually a pretty high-level diagram because each of these boxes has lots of components in it, but those aren't really the point of the Hadoop stack anymore. It's more, if you look at the top, you can see these kind of orange boxes, which are the engines that run on Hadoop. And those are the things that users are interested in, because they provide different ways of writing applications, different styles of workflow. The one on the left, batch processing, is exactly what I just mentioned, the MapReduce processing paradigm. And it's also labeled Hive and Pig, and those are tools that were developed that run on MapReduce, but they're still very batch-oriented. They take large data sets and they take a while to crunch through them. The second engine is interactive SQL, and that's typified by Cloudera's Impala, which allows you to do very fast, responsive SQL over large data sets. So that's a kind of different workflow. The third one is interactive search, and that's similar to SQL, but it's more like a search interface that you're familiar with on Google, for example, where you type in search terms and you can search the data in your Hadoop cluster. And then there's machine learning. There are other ones like Spark, which isn't on this diagram, but is a natural engine, which is an in-memory processing platform and streaming API. So these different engines enable different applications. It's not just batch anymore. Just to go through a few applications, I think people in this room will be very familiar with the style of these applications. I was talking earlier with some of the people in the startups at the Hive, and they're doing applications like very similar to these. So a batch application example would be, imagine you have a huge archive of songs in HDFS and you want to find something out about them. You want to run an analysis that touches every song in the database and comes up with some summary statistic. Interactive SQL, an example would be running arbitrary ad hoc SQL over recommendations that are being streamed into HDFS. Search would be a similar kind of application. Imagine email traffic coming into HDFS and you want to query it in near real time. And then machine learning, an example would be detecting fraudulent transactions using a clustering algorithm. And these are all actual use cases from Cloudera's blog, by the way, so you can, if you look at these slides later, you can read more about some of these applications. So that's my kind of introduction. This is the structure of the talk today. I'm going to go through what a typical application looks like, its kind of architecture. Then I'll introduce the Kite SDK and how it helps build out that application, and I'll do that in an example. And then I'll talk in a bit more detail about some of the kind of special things that we've built in Kite and some of the features that it provides. And then I can take questions. So this is a really simple view of a typical application. It's a batch application, so the first category I talked about, but you can build other types of application with Kite as well. But I'm going to focus on this simple one. And you'll notice there are no Hadoop boxes on this page at all. It's something that you could build outside Hadoop on a smaller scale. And the idea is that it's a web application that generates events. So clicks on a website, transactions, sale transactions, something like that. And there's infrastructure to collect those events. And the infrastructure makes sure that those events are stored in some kind of database, which is shown as a green box here, labeled event data. So that's the store for the raw data set. And we want to build some kind of reporting system that maybe runs every hour and summarizes that raw data in some way that we find useful and stores it in a new data set called reporting data. And the red box at the top is some code that we wrote, the user wrote to generate those reports. So if we zoom in a little bit to look at that in more detail, the Hadoop components start appearing on this picture now. So this isn't actually a Hadoop component, this is just a standard web application like Tomcat. But we have a servlet and we have a log4j appender which will create the log events, will log the log events, sorry, to a Flume agent. And Flume is a Hadoop component that will collect log data and make sure that it ends up in HDFS. So that's its job. The event data we see here is stored in HDFS now. And what we need to do is build our workflow that's going to run every hour. And we're going to drive that workflow using a component called Oozy, which is like a workflow scheduler in Hadoop. And that will drive a workflow, and we can write that workflow in any kind of language we like. Oozy just launches it, and we'll use Crunch to do that. Crunch is a kind of high level, think of MapReduce but higher level. And I'll show an example a bit later. It's a Java API. And the output of this job will be the report, also stored in HDFS. And then to the right, you can see a box which is labeled Impala. Impala is the SQL ad hoc interactive SQL engine. So we can do ad hoc reporting on any of that data that we like. So I had to describe quite a few different Hadoop components in this picture. And so what you could do is go away and write all of these parts yourself. And this is what people do. We have lots of people at Cloudera who help our customers build applications that are exactly like this. This is a really common use case. But the thing is, they have to go and write all these red boxes. They have to, there are some bits in here as well, there's configuration for Flume. They have to know how to tie all of those components together, and that's a challenge. And in fact, that's what we're trying to solve with Kite. Now, if we zoom in even further, no one can read it now because it's too small. But the important thing is, the difference is these pink boxes have appeared. And the pink boxes are some of the infrastructure that Kite is providing to make it easier to write this system. So we have a log4j appender here. We have something in Flume which will partition the data in a predefined way. There are some more Kite components that I haven't actually shown on this slide. So there's some Crunch helper code, there's some Oozy helper code as well. So the kind of picture that I'm trying to paint here is that Kite helps you build systems like this without you having to know about the details of each of those components. So you don't have to know a lot about Oozy, you don't have to know about how Flume works. You can use pre-configured APIs. So now I'm going to talk about Kite and how it, some of its characteristics, and just first of all, how we describe it. Really, the way I think of it is as codifying best practice. It grew out of a team at Cloudera that had a lot of experience with building these customer applications that I was talking about, the ones that were like the one in that diagram. So if we got our kind of best solutions architects, they would build a system like this, and we're trying to take that knowledge and codify it. And codify doesn't just mean writing code and saying, here's an API, just use this. It's also writing tools, documentation, and probably most importantly, examples that people can take and start using, because it does roughly what they need to do. They can take the example and adapt it to their use case, and it's a quick way of getting a system up and running. So this describes a little bit about the history of Kite and what it does. It's really a client-side library. It's not, don't think of it as something that runs on the cluster. The cluster, it orchestrates all those components in that diagram. It orchestrates Flume, it orchestrates Uzi, but you control it from a Java client. It's just a jar. It's almost a year old now. We started about a year ago in February last year, and it used to be called the CDK, which stood for Cloudera Development Kit, but we've rebranded it as Kite to make it more vendor neutral. And we've been doing quite a lot of releases. We try and release once a month. We released version 0.11.0 earlier this month. It's all open source, Apache 2 licensed. It's on GitHub. It's also very modular. We are trying to encourage piecemeal adoption by breaking it into small modules. And the main module that I'm going to talk about today is the data module. And I'm going to talk about how it works and how it interacts with these different components. There are a couple of other modules I'd like to mention. The morphlines module. And morphlines is a way of transforming a stream of records. It will come up a little bit later, but it's a very useful module for doing, for integrating search into Hadoop applications. There's also a Maven plugin which makes some of these tasks more easy to use for a developer. So now I'm going to step through an example. So remember the diagram I showed of the system. I'm going to show how we can build that using Kite. I'm going to show some code. I'm going to introduce some of the concepts in Kite as well as we go along. So the data module has a few concepts. The most central concept is that of a data set. So a data set in Kite is a first class entity. Everything's talked about in terms of data sets, and a data set is a collection of entities, where an entity is like a record or an object in a model. We have a data set repository, which is where the data sets are stored. There are actually two types. There's an HDFS data set repository, so we store data sets on the file system, and there's also an HBase implementation as well. And I'll talk a little bit about the kind of unified storage model between those two repositories a bit later. We also have the concept of a dataset descriptor, which models metadata about the dataset itself, so the schema. Everything in Kite data has a schema, and the format as well. So the format example might be an Avro format file or a Parquet format file. We also have writers and readers to do streaming reads and writes to those data sets. Okay, so that was the terminology. This is some code to actually define the model that we're going to use. We're going to stream events into this system, remember? So it's really easy to define an entity. It's just a plain old Java object. It's a Java class with some fields. Here there is ID, timestamp, and source. And we have a bunch of getters and setters as well. So it's really simple. This is actually, under the covers, this is turned into an Avro schema. And if you wanted to, you could write that Avro schema yourself. But you could equally well just do this. So there are two approaches. It's quite common in object relational mapping systems that you can either define something via a Java class or via a schema. There are some advantages to doing it via an Avro schema, actually, because it's slightly more performant, but this is probably the easiest way to get started. And you can switch between the two as well. So once we've defined our model, the next step is to define the data set. And what this is going to do is store the data set metadata into Hadoop's meta store, which is in Hive. So this is a bit of code. First bit will open up the dataset repository, and you'll notice that there's a URI there. All dataset repositories are referred to by URI, and this is a very simple one. It just says use Hive. You can get more complicated ones that could use HBase or file system in a particular way, but this basically delegates everything to Hive, which is a very common use case. The next bit is to set up a descriptor. We're going to say that the schema of our data is defined by the event class, so the Java class we just saw. And then we can just create the data set. We're going to call it events. We pass in the descriptor. We now have a data set. There is now metadata which describes that data set in Hive. You don't even have to write that code. This is where the Maven plugin comes in. You can use the Kite create dataset goal, pass it a bunch of parameters, and it will just do it for you. So we give it the repository URI, the dataset name, and also information about how to construct a schema. Okay, so this is all set up. We could even look into the Hive metastore to get some information about the Avro schema. This is what it would look like. If you're not familiar with Avro schemas, you can see that they're described in JSON. So JSON is used as the schema definition language. It's pretty easy to understand. It's got an ID, timestamp, source fields, and these are Avro types. So a Java long will map to an Avro long, a Java string will map to a Avro string. It's quite straightforward. So we could have just written this ourselves if we wanted to. Okay. So now we're going to actually put some data into our data set, and it's a streaming example. We've got events that we're generating, and we want those events to be written into the data set. So what we're going to do is actually, the simplest way to do that is to use a log4j logger, which is what that top line is getting an instance of. Then we just create our Java object, which is an event, and we set our fields on it, ID, timestamp, source, and then we can log that event. And this code can appear anywhere. It could appear in a servlet, it could appear in an application, wherever you want to embed that, really. So in our earlier example, it would be in a web app. Okay, so another file. This is a log4j configuration file that basically makes sure that everything ends up in the right place. These two lines say use Flume, so you want your data to go to a local Flume agent, and then Flume will send it into HDFS. And we have to say which data set we're going to send it to. So we're going to use the Hive repository, and we're going to say the dataset name is events, and that will make sure that it ends up in the events dataset. And once we leave it running for a while, we'll see that the events start appearing on the file system, and this is where they will appear. User Hive warehouse is where Hive by default will store its tables. The name of the table is events, which is the same as the dataset name. And some files appear in that directory, Flume data with a number on the end, and those are Avro files with the actual data inside them. So that should give you an idea of what's actually happening on the file system after you've written all that code. Okay, so the next thing we want to do is generate our hourly reports. I'm not going to, this is the most complicated slide with the most complicated code on it. I'm not going to talk about the middle section very much. The point really that I want to make is that we're using Crunch to transform our event object into a summary object, so summary. Crunch you can think of as being a kind of a parallel collection. P collection is a parallel collection. It's like a non-materialized collection of data. And the integration that we've written allows us to open the events data set and read it into Crunch and still use the same Java event class that we defined earlier. Okay, so we read our data into Crunch, which is what this line's doing. It's turning a data set into a Crunch source, and then this bit does a transformation into a summary, and then we write those summaries out into another Kite repository, which is called summaries. So the nice thing here is we can use the same data model that we defined earlier, and we can use it in our Java program without having to think about serialization or partitioning or all those kind of things. We can just think about the domain. Good question?
When you're saying summary, is it like a sum? Is it a distinct? Is it a session level summary?
Yeah, it's a session level summary. If we looked at this, it would be bucketing it by time, I think. Yeah. I think, yeah, sorry, no, this isn't sessions, actually. It's doing number of events by minute of the day and source, so we can have different sources, and we can see which sources have more events.
So what would be an alternative if you don't use Crunch? Is it like just writing regular Java code, or basically, or?
Yeah, so this is an alternative to MapReduce. Like if you wrote this in MapReduce, you would no way fit it onto one slide. So it's much more concise than MapReduce. I'm not having to think about maps, reduces. I'm just thinking about this bit is where all the kind of transformation happens. And if you think like grouping, parallel iteration, yeah, those are the two operations there actually. But you can, the nice thing is you can make this arbitrarily long. In MapReduce, you have to think of one map, one reduce, and then the next map, the next reduce, and you have to kind of pipeline those yourself.
Is this using Hive at all or not?
So this isn't using Hive, but it is writing into a Hive target. So when I write this summaries collection, it's going to go into HDFS, but the metastore knows about it.
The reason I asked is because you could have used Hive as well.
Yeah, you could. I mean, you could use Hive. You could write SQL to do that transformation potentially. There are lots of things you can't. Lots of, analyses you can't express very easily in SQL. So Crunch is used a lot in machine learning because you can put arbitrarily complex analysis in this step. Okay. And this is the mechanics of how you would run it. Again, you can do it through Maven. So the first line, just very briefly, is creating the summaries data set, a bit like we created the events data set earlier. And this part is running that program. And the nice thing is, one of the kind of pains of running MapReduce and other tools is that you have to get your class path right, you have to build jars, all those kind of things. We've built some Maven plugins that will assemble all of the correct jars and run them for you just by typing very simple commands. And this will actually run it locally. You will launch it locally and run it in a cluster. You can also have the option to launch it from the cluster. And you can also run it periodically as well. So we're supporting all of those different kind of execution options. So you asked earlier about, is it writing to Hive? So this shows you that you can actually query these data sets using Impala. And that's because we're storing the metadata in the Hive metastore, and Impala can read the Hive metastore. So from Impala's point of view, if we describe the events table, we'll see its view of the schema. So we see the same fields, ID, timestamp, source. We see the types are actually Impala types now. So long has become big int and string is string. So this is really nice that we can, without doing anything extra, we can query the same data set using a different tool in the Hadoop ecosystem. And we can do an ad hoc query. Here we're just going to count the number of events by source. So that was a bit like the bucketing example, but using Impala to do it. A small data set, but we can run this on much larger data sets, and it's very interactive. Impala's been designed to be a very interactive system with low latency. It also provides a JDBC driver, so we can run those queries from JDBC just using standard JDBC APIs. You use a connection string like that, which is a Hive driver, and that will be supported by Impala as well, and you get all the speed advantages of Impala as well. So that was how you built, how we would build the typical example I was talking about earlier. There wasn't a ton of code there. Obviously, I had to take out a little bit of boilerplate, but I think you can see that building an application is fairly lightweight. The amount of code you have to write is fairly low. Now I'm going to talk about a few of the kind of more interesting advanced features in Kite. Yeah, are there any questions?
That key collections thing in that Crunch slide,
Yeah.
Is it part of the Kite SDK or is it part of Crunch?
It's part of Crunch.
So then where is this Kite addition or what is the value add that I'm trying to understand?
Let me just go back to that slide. So the value add is that we can operate on a data set. So if you look at this part here, repo load events, that's loading a data set, and it's turning that data, and then the as source method is turning that data set into something that Crunch can understand.
So you extended Crunch?
Yeah, we've provided implementations of Crunch, source, and target that are data sets. So that's what I meant about a data set being this first-class citizen. It's an entity that Crunch can operate on, and so can Impala. That's the point.
It's somewhat similar to Spark also.
To
Spark.
Yeah, it is actually. I mean, data set is like a Spark data set, and we haven't done any work on that, but I think it would be very natural for us to expose data sets as Spark RDDs, they're called. Yeah, that's a good point.
Do you see Kite mainly useful for new projects, or you could see that you can take your existing data and you can retrofit it into a Kite data set? Say if you have HBase, a bunch of HBase tables, and you have a bunch of cells which are our objects already, is there a way to say, okay, let's treat this table as a Kite data set and do something Kite with it?
So in that example, with an HBase table, I would say it's unlikely that they're serialized in a way that Kite would understand.
But if you do have, if your cell is an outer object already,
Yeah.
or there are additional things that Kite does in a way that it describes table, names them, names cells, etc., etc.
Yeah, it has a particular way of serializing them in the Hive. In HBase. So I doubt that you'd just be able to read that from Kite, but we do have some examples where you can convert existing data sets into Kite-aware data sets.
Do you have the documentation of all the Kite internals, how it represents the data? I mean, I'm sure it can be read from the code, but do you have a more clear?
Do we have a document on? I don't think we do. No. I think we need one. So yeah, I'm going to now talk about that very topic actually, which is the unified storage interface. Everything I've talked about so far has been the HDFS storage layer. So we're talking about data sets, we were talking about streaming access, where we were writing events as they came in. That's a very natural HDFS pattern. We also have a subclass of data set called random access data set, which, as the name suggests, allows you to do random access, and it's backed by HBase. And what we've done is allowed you to use the same Avro model. You can use the same Java classes and the same Avro schemas to store data in either of these two types of data set. And that allows you to build quite interesting applications, I think, potentially. You can, because they have different access patterns. Data set is for streaming reads, whereas random access you can do point lookups. And to make that work, we have to figure out a way to, because they're different, because HDFS stores things in partitions. So the partition would be, for example, a day's worth of data. Whereas HBase has a different way of representing things. HBase has row keys. And you scan through tables. So they have different physical storage characteristics. And the way we abstracted that is by having this thing called a partition strategy, and that defines how an entity is mapped to one of those things, how it's mapped to a partition or how it's mapped to a row key. And here's an example of how you can do it for HDFS. We can define a partition strategy which says, take the timestamp from the entity, and we're going to partition by year, month, and day. And what that does is look at the timestamp, and it knows how to convert a timestamp into a year, and into a month, and into a day. So that will form, on the file system, a directory structure that looks a bit like this. So before we didn't have this highlighted line. Remember, we just had our Flume data and we didn't have any partitions. But now we've partitioned it. We've got this structure where you have year equals, and then the actual year, month equals, day equals. And that's the way that Hive does partitions. So what we've really done is defined a partition strategy in Java, and that's now been stored in Hive, in the Hive metastore, so that Hive applications can understand it. So in Parler, for example, querying this table would know about the partitions. Hive would as well. And we can do a very similar thing in HBase. For this example, I've shown the user entity, which has got two fields, username and favorite color. And username is a key, so in HBase that would be stored as a part of the key. And the favorite color is not a key, it's just a regular column, so that would be stored in the column data. And by the way, this is in HBase is the column family and the column name. We could have defined it using this same partition thing, but we haven't quite implemented that yet. But the idea is that you'd be able to define partition strategies for HDFS and for HBase in the same way. So just briefly continuing with this example, which is a user example, and our key is the username. This is how you would create and use a random access data set. You would create it in a very similar way. We've got this URI here, which is basically an HBase URI. And instead of getting a data set repository like we did before, we now have a random access data set repository, which when we load the user's data set, we get a random access data set. Okay? And we can put new users in. So I've put in a user called Bill and a user called Alice. And then the next stage is to retrieve the data, and we can do that by constructing a key. We set the username there, and we can retrieve the user called Bill using the get method. So this is in addition to the streaming interfaces that we support. So you can, with a random access data set, you can do puts and gets, and you can also stream. Yeah.
What would be the pros and cons of using directly the HBase API versus going through this route?
So if you use an HBase API directly, you have to do the serialization yourself. You have to figure out how to serialize your data. So the equivalent in HBase would be if you called get, you would get some bytes. You wouldn't get a user object. So another feature we've built is something called views, which is like a restriction of a data set. And in this example, we're going to restrict the data set by saying, take the user's data set, but only return me a view of everything that, of all usernames that start with Bill or anything after Bill. So anything, beginning with C, D, E, etc. And then what we're going to do is create a reader to read through all of the data in that view. We just iterate over the users and print them out. The important thing about this is that it will only return Bill. It won't return Alice because we've just restricted it to all users Bill and later, and Alice obviously is earlier in the alphabet. And the nice thing is that, again, this code would work for HDFS. So if you think back to the events example, you could imagine specifying a view that was just a particular date range, maybe just a single day. And you could use the same code, you could restrict your events data set and say, I just want to look at this part of the data set, and then you could iterate over it in the same way. So again, we've kind of unified those APIs for different storage backends.
So what is the motivation for this project? If you look at a figure, people try to invent new language, try to lay the abstraction level on top of Java or whatever language typically you're coding for MapReduce.
Mm-hmm.
What is the goal of in terms of bigger picture?
Yeah, the idea is to make it easy to model your entities that you're working on.
Can you repeat the question?
Oh, sorry, yeah. The question is basically what's the high-level motivation for doing this unification? And the answer to that is we're trying to make it easy to model the objects that you're working with and allow you to combine different types of data set in the same application. So having like a cache, the cache could be stored in HBase, and then you could have the archive data in HDFS, and those could be the same. They could have the same model, and you could do some clever kind of you could kind of combine those two data sets.
Yeah, so I understand. So definitely there are different kinds of ways on to accomplish this goal. Do you think a new language is necessary to do those kind of things?
So this isn't a new language.
A new language?
No, this isn't a new language, is it?
This is a new language?
No.
No. Yeah. So I'm asking you. Do you think a new language like?
No. I think.
Is necessary, or this approach is better? There you can compare different kind of.
Yeah, I don't think we need to invent new languages for these things. I think we should use existing languages that people are familiar with, like Java and Scala and Python. So one of the goals of this project is to make it possible to use all the different processing engines in Hadoop to process these data sets. I showed how we can use Crunch, we can use Parler. That we also want to support MapReduce actually. So what I've got here is Crunch and whether it supports parallel processing on HDFS back data sets and HBase back data sets. And the answer is, so we started with Crunch because we like the kind of high-level nature of it. We support that for HDFS data sets. We're working on support for HBase data sets. We're also working on support for MapReduce because obviously MapReduce is very important because it's used by lots of different tools. And yes, we support Impala and HDFS, and at some point we want to get it working in HBase. So the idea is we want to fill out this matrix and get it working for all different tools in the ecosystem.
Is there any data on the performance of coding through this API versus going to the native HBase or Hive APIs?
Well, so if you're doing a similar thing, I think it would, like if you're trying to create objects yourself, then you'll have the same overheads. If you're doing lower level stuff, like you're representing things in binary formats, you might get better performance.
Using the native APIs?
Yeah. So another aspect that we've thought about is Schema Revolution. It's very common, it happens all the time obviously, that you change the structure of your model, and here we want to add a new field. So we're adding a field called IP address, and Avro has a set of rules that dictate how you can evolve your schema. And what we've done is built into the tooling, so this is the Maven command. If you want to update your data set, you call Kite update dataset. And we've built in validation to make sure that when you change a class, that it conforms to these rules. And in this example, if we'd missed out this nullable annotation here, it wouldn't have allowed us to update that data set. And that's because if you add a new field, you have to specify a default. And we do that here by saying nullable to say that the default is null. So we've got that built-in checking. So you can't just change your schema in such a way that it's impossible to read old data. Because if we didn't have a default value and you try to read old data with the new schema, then it wouldn't know what that new value is for the old data that you loaded, because that field wasn't present when it was written. So we've got tools and we've got the rules for that. So this is how we integrate search. So I talked about search at the beginning, and the idea here is that we're going to enable near real-time search. And the way we implement that is by having a special sink, which is a Flume Solar sink. So in the original diagram that I showed you, all of the data went straight into HDFS from Flume. In addition, in this scenario, we send it all into HDFS, but we also send it into Solar. And so this is the Solar sink here, and then it goes through this kind of pipeline, which is a morphline transformation pipeline. And then when it gets into Solar, Solar will then index it and write those indexes into HDFS. So this is the morphlines library I talked about earlier very briefly. It's basically a set of different commands, so we can do things like read records, match patterns, and then load those transformed records into Solar. So it basically allows you to specify which fields are indexed in your processing. And then the nice thing about this is that Solar Cloud will run on the Hadoop cluster that you've got running, and the indexes are served from HDFS. So the whole thing is built into the Hadoop cluster, and it's just regular Solar from the point of view of the APIs. It's just a Solar API, and so you can use any of your search tools that interact with Solar against this cluster. So morphlines is a part of Kite, but in the future we want to make it much easier to make everything just searchable by default. You would basically configure in some way the fields in your model that you want to be indexed, and Kite would automatically do this kind of transformation in morphlines for you. So then you would just load data, and then you'd be able to do arbitrary searches over the fields that you've chosen to index. Okay, so those are the advanced features I wanted to go through. This is my kind of summary of what Kite is. It makes it easy to get data into Hadoop with a flexible schema model that is storage agnostic, so you can use HDFS or HBase in a format that can be processed with a wide range of Hadoop tools. So we saw some of the tools like Crunch, Impala, or others that we could use. And this is my last slide about how to get started with Kite. You can go to the website, but we've got lots of examples. I mentioned the kind of importance of examples earlier. We've got examples that show you how to work with streaming and random access data sets, how to log events to data sets from a web app. So that was the example I was talking about earlier. You can run periodic jobs. There was a question earlier about using existing data sets. We haven't done a lot of work in that area yet. We want to make it possible to read existing data sets. And we've started by looking at CSV files, so you can view a CSV file as a Kite data set. And things will just work, so it's like a read-only view of an existing data set. We've got code to convert Avro data sets to Parquet data sets. Parquet is a column-oriented format. We've got examples of morph lines, various examples for writing and configuring, and also how to write JSON records into a data set. So we've got all these different examples, a growing set of examples that you can get started with. Are there any questions? Back.
My question is, so for creation and populating data sets, you seem to rely heavily on Fluke.
Yeah, so that was just the example.
Yeah, so for example, you use Crunch to summarize events into summaries.
Yeah.
If I want to make those summaries searchable, how do I do that?
So as I said, you can't do that today with the way that with the code that we've got so far. You would have to use morph lines allows you to make things searchable by sending it to a Solr sync. So to do that today, you would have to integrate morph lines yourself. You could possibly do something like this. You could put morph lines into your pipeline so that it can do the indexing. But I think your example there is something that we want to add better support for. You can't really do it very easily today is the answer.
Good question. What's your thinking on, you have this abstraction about Avro versus Parquet and when that decision gets made to convert, like if you just write
Yeah, I didn't actually talk about that at all, did I, until the end. So all of the examples I gave so far were about Avro, and Avro is an excellent row-oriented format. I should say, actually, there are two Avro things. Avro is the schema definition, but it's also it's the container format for files as well. So you define your schema in Avro, and then when you write the data, they are written as Avro data files. There's another format called Parquet, which is column oriented. So when you create a data set, you can say whether you want to store it as Avro or as Parquet. So you have to make that decision yourself. We haven't got any kind of heuristics about in the code. I mean that says, oh, that's the read pattern for that one is it's only going to read a few columns, so we're going to use Parquet because they're very wide data sets. You have to kind of make that decision yourself.
Do you think eventually they would ever fall under the we'll handle that for you, or is it kind of always going to be?
I don't know, possibly. I think the other thing about Parquet is you can't have Flume produce Parquet, so there are technical reasons why that doesn't work very well. So this is why we've got this example, because you might have your Flume sync will write Avro format data, and actually it's it's very wide, and you want to use Impala on it. So Impala and Parquet work really well together. So we want to do this conversion to make it very efficient for Impala. So we stage in Avro, and then we write to Parquet.
So the kind of follow-on question to that then, so do you think about for the morph lines doing it in that step, since you're doing that conversion step anyway, to stick it there versus having morph lines do it in Flume and Flight?
Yeah, so the problem with writing Parquet in Flight is that you're writing a column-oriented format, which is very heavy on the buffers. So what we're thinking of doing is, rather than doing that, we would have a periodic job that runs on a fairly small frequency that would convert them. So you'd have, most of your data would be in Parquet, but the most recent data would be in Avro, and then it would be converted.
But in that step, could you do the morph line convert? Like if you had just raw data coming in and you want to change it to a certain schema.
Yeah, you could put morph lines in there. Yeah, definitely. Yeah.
So overall, what is the biggest challenge for Hadoop project ongoing, day in and day out? What's your
in general? What's the biggest
what's
challenge
the
for a Hadoop project?
right now.
That's a good question. I don't know. I think some of the things that people have struggled with is definitely how to get started. It's like, because there are now like a dozen components in the Hadoop ecosystem, and trying to understand what each of them do and how you make them work together I think is a challenge. How you get your data in and how you start analyzing your data, I think, has been a challenge in the past. I think the tools are a lot better now than they used to be. Yeah. Question?
As a data scientist, I really appreciate the Kite let user focus on these logic entity instead of dealing with readable, writable. But to separate the question before too much to ask, is there a Python interface or Python streaming thing?
No, the question is there a Python interface? We've only focused on Java for this. I mean, we don't rule out doing other interfaces like Python or Scala as well, but we haven't had time to do that. Not yet.
So just continuing on the part about the mix is a big challenge. There's like there's all kinds of components that do all kinds of things. There's overlap. In fact, I was at some point, if you try a Venn diagram, they're kind of all over the place. So if you now CHD tries to solve that problem to some extent, kind of tries to give you a parity between what works with what. And then there's Big Top, which is, I would, if there is a way to spend some time comparing the two distributions to see why would you use one versus another, because that's a big challenge for somebody who's trying to start. I don't know as many people have tried it. I mean, I've tried it. It's a big problem to figure out what works with what. And
sorry, compare what and what?
Like CHD versus Big Top.
Oh yes, CDH. Yeah, Cloudera's distribution of Hadoop. Yeah. So one way of looking at it is the Big Top is the open source Apache project that selects a different stack of components with different version numbers, builds them together, runs a few basic tests on them to check that everything works. CDH is derived from a Big Top base, as it were. So the Big Top's a bit like Fedora, and CDH is a bit like the Red Hat model, because it has, so it takes Big Top and adds more patches. Big Top never does patching. It just takes the base releases from the Apache project and combines them and tests them. But CDH will add patches for security, bug fixes, small features.
And so it's a one-time cut, or is it cut every time? Like if every CDH version 4 or 5 takes the latest release of Big Top?
Yeah, it will start from a, it will, so say Hadoop went from version 1.1 to 1.2 in the next, it would reflect that in the, it might use the newer version in the next version of CDH.
Question on the scope of the SDK. naturally for solar. So right now the problem is, I think now Hadoop as Cloudera itself says, is not just MapReduce, it's getting the impact like for solar, and you have this machine learning. So how do you keep track of all those different things? Do you have intentions of like ML extension, machine learning?
Yeah, I think we do. We want. So I mentioned some of the morphline support for search and how we can improve that in Kite, so that you have to do less configuration work yourself. So that would cover search. For machine learning, there's a whole other set of projects actually for machine learning. In Cloudera, there's Oryx, ORYX, which is a project that's built on top of Crunch to do machine learning tasks like clustering and classification, and then to serve the results of those outputs. So those projects are really suited for machine learning. And I can see in the future some integration between the dataset work we've done and some of the tools we've built and that project. And then the Spark, which I mentioned at the beginning, as being something that we'd like to be able to use. I'd like it if people could use Spark to operate on Kite datasets. So yeah, there's definitely more integration work with those engines that we want to do.
Is it supported anyway by Cloudera, or is it Apache general?
Which project, sorry?
The Kite.
Kite is supported by Cloudera, yeah.
So for developers, what would be your suggestion? Like, continue programming using the base code APIs, or to move on to this? Like, how do you see that?
Well, we think that this is a much nicer programming model for developers. So, yeah, we want people to start adopting this API, yeah, this way of working with data sets. I mean, we chose Avro as the core schema definition model, but as I showed at the beginning, you don't have to interact a lot with Avro if you don't want to. We're trying to make it as approachable as possible. Yeah, while a lot, we're using. So Avro has been around for a long time. It's pretty highly optimized now, so it's pretty efficient. So we think that it's a good technology for this kind of project.
So you think this API is just specifically for Cloudera API, or this API is a public API?
No,
I mean, suitable for any kind of Hadoop distribution.
Yeah, it is suitable for any Hadoop distribution. We recently added a patch that supports Hadoop 1. We're working on it supporting general Apache, so you can run it against general Apache.
How about those, Amazon AWS EMR? Because they use three of those 5 versions, they use MapR. So will MapR support those kind of APIs?
We're compiling against core common Hadoop APIs, so it should work against that. It should work against EMR. We haven't tested it on that, but there's no reason. We haven't built anything in it for it not to work against that. We're using standard core APIs in Hadoop.
So like Cloudera Navigator, and I mean I've seen like, there's not a lot of open source versions of that yet, but like basically having a dependency graph of where data came from, and where it's going, who's used it, that type of thing. Is there any thought of how that integrates with this? Or?
Yeah, we haven't looked at that yet. It would be a natural thing to do though, like how we can integrate with data lineage and those kind of things, either in Navigator or in open source equivalents.
Is there an open source equivalent?
I think Falcon does something similar.
So according to your experience, suppose we have 2 options.
Yeah.
Try to simplify the problem or lay the abstraction. One is a new language. I mean, a much simplified higher level language. The other is API. This approach is different API approach. Which one would you like to go? Typically? API.
Yeah, I think I answered that before.
Okay, cool.
You want to invent a new language, I think. I look forward to reading
I understand.
it. Okay. Any more questions?
Is there a plugin or designer tool to use this?
No, there's not. I mean, the only developer tool integration we've done is with the Maven plugin, but there's no kind of visual tool now. No. I mean, we want to use standards like Java Beans and all of those kind of things. So existing IDE should support you in that.
But with the architecture, you can easily have this kind of plugin to.
A what plugin? Sorry.
Like an Eclipse plugin to basically.
Oh, I see. Yeah, we haven't done anything like that.
Of it, right?
There's an Apache project actually called Hadoop Developer Tools, which is developing Eclipse plugins for. I haven't looked at it lately, but I think you can do things like write MapReduce jobs and those kind of things in the plugin.
Because I'm trying to understand how much higher level do you want to upscale to. Instead of people knowing the schemas and everything, can you look into it and abstract features to
Do you mean
writing my own bean over here? Is
Yeah.
there a way to abstract to look into the data itself and create that bean or something
Learning
in that level?
learning code can be
Definitely
very
build
steep.
higher level things on top of this. I think. I mean, we're trying to build a framework and an SDK so that people can build on it. So tools like that would be.
I mean,
sounds like something you could add to on top of the project.
it really depends on the complexity as well as the usability of your API. For some API, learning curve probably gonna be very steep because I have to know a lot of things.
Yeah.
I mean, there's a pro and a con.
So it's a pretty small API as well.
Yeah.
We've tried to
if
keep
you
it
can make
small
them a
and simple.
minimum,
Yeah.
that'd be cool.
Okay, I think that's it. Thank you very much, everybody. Cool. Thank you. No, it's fine actually. I think it was audible.
Yeah. Yeah,
you're completely right. Normally I would struggle, but it's
I have so many, that's why I didn't.
Yeah, no, I thought people can come up afterwards. Yeah, as long as you're not going to ask me to design it.
Oh, no, this person actually has it. I've seen them.
I haven't.
No, it's fine. Yeah, it's fine. Yeah, but
yeah.
Hello, how are you?
That's fine.